I'm just making sure that the Zoom is on, okay? Because I'm using Zoom to do recording. There we go. All righty. So it is recording. All right, so that's the exam. That's the practice exam. We're not going to go over the practice exam, not today for sure. Probably by next Tuesday. Okay, so I think we can cover the material necessary and talk about this on next Tuesday. But it doesn't mean that you don't want to take a look at this. I would still take a look at this just to understand what is going to be on exam 1. So when I do cover that material, you will connect it not only to just the lecture material, but also to the exam questions themselves. So that you can look at this as a prompt of what you should be focusing on or what you should pay attention to as we talk about those further topics. So there's that. And I sent out a whole bunch of stuff, in the announcements. I'm not sure whether other professors utilize the announcement for this much, just spewing out stuff. There is the carry look ahead adder for today's lab. So this is an attachment. So for today's lab, you kind of have to start with a file that you were supposed to end up with on last Thursday. For those of you who are not really sure whether your design is supposed to work or not, or whether you could make the necessary correction to get it to work or not, you can always use mine as a starting point of today's class. And I can also tell you that I finished enough of this lab so that question number 1 of today's lab is pretty much all done. So there you go. Do we have any questions about the lab from last Thursday? No questions. All right. So a few key points. The circuit names are case sensitive. So lowercase k and uppercase k are not the same. Okay, so kind of keep that in mind. And then also the relative positioning of the input pins are important. So if I have P on top of G on top of K0, you need to maintain that relative positioning. Now, does it have to be exactly like two of those squares below? No. Okay, but they do have to follow the same order on the left-hand side. And on the right-hand side, we only have 1 pin as an output pin. So that is not as much of an issue. I did not deduct a lot of points, okay, for designs that do not work with a test writer. I just deduct, like 1 point out of 4. I don't consider that a lot, okay, because of the way I scale, the scoring of this class. So there's that. I'm not sure whether this is helpful or not. You guys can tell me. A concept review of today's lecture. So if it is useful, I might continue doing this if I remember to do it. If it is not useful, then I probably won't be doing this any further. When no one seems to be benefiting from this. So basically, I just outlined all the things that we have talked about and all the things that we will talk about in boldface. So this way, if you just read this, maybe half an hour before class, you can kind of just remind yourself, what topics we have already started to talk about, and what to kind of quickly review and stuff like that. All right, so that's a quick rundown of the announcement since last Thursday. And then what we're gonna do today is to continue. I'm just double checking and make sure that Zoom is running. And I want to make sure that no one is trying to get in. That is correct. Nobody is trying to get in. So everybody is supposed to be here in person. Excellent. So now we can go ahead and talk about the new topic, which is subtraction. All right. So we're going to start with an example of what we talked about last time. So last time we already talked about the R function, which is the single digit difference this time for subtraction, as well as the borrow function. Do you guys still remember how those two functions are defined for base 10? Okay, and I think we also know how to convert those functions to work with other bases. So what we'll do is we're going to do a base 7 multi-digit subtraction just as a quick reminder of how those rows are related to each other and how we use the R function, the single digit difference function, as well as the B function, which is the borrow function. So we'll go ahead and start with that. There are several ways for me to do this. One way to do this is to use a Google Sheet. Okay, I know this is a total overkill to use your Google Sheet, but hey, it's pretty handy to use in the class, and I can share that with you like right away. So if you go to the share folder, as soon as I create this particular Google Sheets within the shared folder, you can see it. So I'm going to name the sheet the same as today's date. So I'm going to put in 2023 0207. And you should be able to see it now. For those of you who want to use your own device to look at the spreadsheet, you can do so. Otherwise, you can just look at the screen, and all of this is getting recorded. Okay, so no need to frantically copy stuff, just focus on the concepts. All right, so that being done, I'm going to start up Zerno, not Zerno, but Joplin, because I kept my notes in Joplin. So it has a copy of what example I want to use in class today. All right, so Joplin is up. Let me show you Joplin on this side. There we go. All right, so the example that I want to use is 204 in base 7 minus 105 in base 7. So 204, 105. All right, so let's switch back to the Google Sheet here. So we'll start to, I'm gonna put the digits over here. The first one is what, 205, or did I? 204. 204, okay, 204 and then 105. 105, and this is a subtraction, so I need to make sure that we remember that this is a subtraction. And one thing we can do is to kind of make the columns a little bit narrower, because otherwise it's just using up screen's space unnecessarily. But I can zoom in a little bit more so it's easier for you guys to see what is going on. And typically we can also put an underbar below this row of cells. And let's see, where's underbar here? So this is just underbar like so. And this is the row X. This is the row Y. This is still called the row Q, okay? And there's a reason why I kept the term Q in this case. This is now row T, and this is row D because we are dealing with subtraction. So now we have another underbar that we need to put here. There we go. And now we can do the actual computation. All right. So what is the single digit difference between 4 and 5? 4 minus 5, but in base 7. Okay, so you have to remember how the R function was defined for base 10. You go like, okay, we're not dealing with base 10 anymore, but we're dealing with base 7. The only thing you have to change for the R function is to change the constant of 10 to 7. But you kind of have to remember the rest of that function. So what should I put here? It's 6. 6 is correct. So now, if you're saying, but I cannot remember how that function was defined, it's okay. I can tell you exactly how it is defined. So I'm using a spreadsheet formula in this case to do all the computation. So it's going to be this cell plus minus this cell here. And then I'm going to plus 7 because I don't trust mod can do what I think it should be doing. And then we're going to mod this whole thing with 7, which is the base that we have chosen to use. And mod is not mode. To get rid of the extra E. And there we go. We have 6 here. Wow. Okay, and then T0, just like K0, unless we are daisy chaining the subtractors, by default, it has a value of 0. And then here we have D, which is also the R, but this time it is the R between the Q and the T. So we can basically just copy and paste this function here. So watch, copy, paste, and we're done. Are we good so far with this part? So the next thing we need to do is to work out what is T1. Okay, so T1 is basically the borrow bit for that particular column. But I call it T because T stands for take away something, because I cannot use B again, because B is the name of the function. So the question now is, what am I supposed to put here? So that equation or the formula to calculate T of I plus 1 is already in the notes. Do you guys remember what it is supposed to be? Well, we have to apply the borrow function, right? So what is the borrow function? Yes.
What's the borrow function? What's T minus?
Well, let's talk about the borrow function first.
If X is less than Y, then return true, return 1.
Yep, that is correct. But the spreadsheet does not have a borrow function. What are we going to do? Well, we can expand the entire thing twice, which is copy and pasting code. That is not a good way to do things, right? So what I'm going to do here is to go to tools, not tools, data, extension. There we go. We go to extension, and then we can go to macro. Nope, app scripts. Okay, we go to app scripts. So here you can define your custom function in JavaScript. And we'll just say this is the borrow function. Give it a full name. And then we have XY. And then we just apply the function that we have already talked about, which is if X is less than Y, then return the value of 1. Otherwise, return a value of 0. And because this is JavaScript, the semicolon is optional. You actually do not have to end a statement with a semicolon like you do have to do in C++ as well as Java. But just so that you guys look at this and go like, this is much more comfortable, I'll put a semicolon in. All right, so with this done, I have to do a Control-S to save the script first. And then I can switch back to the spreadsheet because now I can actually use the borrow function as if the borrow function is a built-in function. So now I can say, okay, make sure that I made it right here. Okay, so now we can say this is the borrow of this cell minus this cell here. And then we would use a regular plus. Okay, this is just a regular addition of the borrow. Oops. Of this, which is our Q0 minus the T0, which is going to be E4, the cell E4. And then press the enter key, and it does the computation for us. Isn't that cool? I think it's kind of cool. And you'll be surprised, what you can do with a spreadsheet, especially in the second half of this class, because I wrote an assembler using Google Sheets and a little splash of JavaScript. Because I couldn't do it without a splash of JavaScript, without making it really kind of cumbersome and not elegant. But anyway, that's for later on. All right. So now we're going to have to work out the other bits too, right? So we have to work out Q1, Q2, T2, T3, as well as D1, D2, all of those bits. But once we have the formulae already set up, it's super duper easy because all you need to do is to say extend, and then we extend again, and then we extend again over here. Of course, the question is, does it make sense? Okay, so you need to double check. So this is the kind of job that I think there will be employment opportunity. It's not so much to do a lot of coding, but to quality control ChatGPT and other types of AI product, because you can't really quite depend on an AI product to quality control itself. That probably would not be a very good idea. So they will need people. They will need people to do that, right? So I think if you keep an eye on what ChatGPT or Codex and some of the other engines can do, you can kind of think about, okay, so if I was hired to quality control the output of these specific tools, how would I do that? What do I need to know to do that kind of a job? So not related to this class, but sort of related to what we are doing here. All right, so I'm going to do this manually now. 4 minus 5 is a 6 in base 7. 6 minus 0 is always a 6, regardless of the base. 0 minus 0 has a single digit difference of a 0. 0 minus 1 in base 7 is a 6 with a borrow of 1. 2 minus 1 is a 1. 1 minus 1 is a 0. There's nothing to contribute an overall borrow here. So I have just kind of did a quick check to make sure that the calculation was correct. Once again, just like what I did in addition, I want to double check this, okay? So one way to double check is really just to go back with all those steps and double check that you not make a mistake in the execution of those steps. But what if the concept was wrong? So if the concept was wrong and I retraced exactly the same steps, I would have made exactly the same mistake. So I need a different way to do it. So I need to convert 204 in base 7 into a base 10 number, convert 105 into a base 10 number, and then do the subtraction in base 10 and see if 066 converted to base 10 is the correct difference in base 10. That's another way to double check this. Okay. It's also a great opportunity to kind of refresh our skills in base conversion. All right. So let's see how we can do that. So I'm going to use equations again, and this time, this is going to be whatever this thing is times 7 squared. So there are several ways to do this. This is not really the best way, but it worked. And then we have D1 times power 70, and then plus E1 times power. Oh, I got it wrong. Okay, the 70. This one is supposed to be 71 because it is digit 1, not digit 0. So that was my mistake. There we go. So 102 in base 10 is 204 in base 7. And then now I can just do this. And then we can do it one more time with the D. All right. Well, looks like everything checks out, right? 54 plus 48 is indeed 102. So unless I make some really, really strange pair of mistakes that kind of cancel out each other, I'm pretty sure the math is all correct. It's all working out. Are we good so far? Does everybody kind of understand what this spreadsheet is about? You already have access to this. You can make a copy, okay? Just in case you say, well, if Jack changes his mind and decides to delete this spreadsheet, I don't have a copy of that. You can make a copy right now, okay? I don't plan to erase this. Why would I want to erase it? If it's only referring to material that we have already talked about in this class. But this is one way to use a spreadsheet. I think you might find spreadsheets to be much more useful than you previously thought it would be. Many of you probably know that we have CISP310, which is a Excel spreadsheet class. I mean, most of you are not going to take that class because you may not understand that spreadsheets are very, very useful, even in programming classes, because it can help you check the results of the calculations for sure. All right, so are we good so far with multi-digit base 7 subtraction? All right, cool. So what I'll do is I am now going back to the extension, because instead of using my own way, just replicating the equation, I'm just going to say function R, xy, and we already know what this is, okay? Because I just put in the entire expression. This one is just going to be, whatever the base is, which I think in this case is 7 plus x minus y, and then you take the entire thing, and then you mod this with whatever base we choose to use. So I'm just duplicating that function definition over here for only one purpose, which is what do we do when we want to perform multi-digit subtraction in base 2? So not taking into consideration that we want to convert everything into transistors. If we're just looking at it from the perspective of calculation, the easiest thing to do is to look at this screen here and say, whatever is a 7, change it to a 2. Right? That would serve the purpose of you figuring out how to do multi-digit base 2 subtraction. Are we good so far? All right. So we'll go ahead and just kind of work out all the different cases. I cannot do it here because otherwise the spreadsheet is going to be wrong. So I cannot do it here. All right, but I can use comment here. Okay, so I'm going to use comments here to kind of illustrate in base 2. I want you guys to kind of figure this out by hand. Now you can see that borrow does not change. Okay, so borrow has never changed. So if you subtract 0 from 0, what would be the result of borrow? In base 2, well, it doesn't matter what base it is, right? It's going to be a 0. Okay, so we'll just kind of work out all 4 cases here, and that is going to be a 1. Okay, very good. And what about this one? Going to be 0. And then what about this one here? Going to be 0. Okay, well, those are the only 4 cases that we can have when each digit is binary or be base 2. Because in base 2, each digit can only take on one of 2 possible values, which is 0 or 1. Is that okay? So we are now done with the borrow function. We don't quite know what binary boolean operator to use in this case because there's no single one that is actually useful here. But we can work this out. Okay, we can work out the expression that can do this. So we'll move on to R, but only for base 2. Okay, so R in base 2. So we'll work out the same 4 cases. What is R00 in base 2? All right, that's an easy one. And what about R of 01? That's going to be 1. Very good. What about R of 10? That's going to be 1. And then what about R of 11? All right. Haven't we seen that before? That's exactly the same as the R function for addition. So in base 2, the single digit sum function works out exactly the same as the single digit difference function. And that's why I kept the name of R. Is that okay? Wait, so doesn't that tell us what logical operator we can use to implement R? Which one is it? Exclusive OR. Okay, there's a long way to spell out the exclusive OR using not and or, but we'll just call it exclusive OR. It's the same exact R function in base 2 for addition. So that's an easy one. All right, so we'll go ahead and make a note of that. Okay, so we'll say R of xy in base 2 is really just x exclusive OR with y. Or if you prefer the not so easy way to express the same thing, you can say it is not x and y or x and not y. Well, I'm mixing up the operators, so I might as well change everything to the C++ notations. So there we go. All right. Okay. Now the harder one is the borrow function. So the borrow function in base 2 only has one case, being a 1, which is when x is 0 and when y is 1, right? So one way to generate a conjunction, that is true, but only when x is 0 or false and y is 1, which is true, is simply to say, we're going to negate the one that is 0. So that's x, and then we'll do an and with the other one, which is a 1, which is y. So not x and y is how we can use binary Boolean operators to take care of the borrow function. But how do we know this works? I mean, it sounds good, right? It sounds like, it's going to work out for the one case that I want to end up with a 1. But how do I know this is going to work out for the other 3 cases? Exactly. The truth table will convince us that this will work out for all 4 possible cases, and we're good here. So are we okay so far with both the B function, which is figuring out do we need a borrow of 1, and also the R function, which is returning the single digit difference in base 2, which turns out to be the same thing as the single digit sum in base 2. That's good. All right. So now we can go back to the notes. Okay. So let's go back to the notes, which is subtraction. Where's subtraction? Binary subtraction. There we go. All right, so it's the same thing, except these are in uppercase instead of lowercase. I probably should change it all to lowercase, but it's the same idea. And then now we use logical operators instead of arithmetic operators. That's what section 4 talks about. And now we can talk about, borrow propagation. So borrow propagation is kind of the same thing, where t of I plus 1 depends on t of I, just like k of I plus 1 depends on k of I. So it's chained exactly the same way. So now the question is, well, can we apply the same technique that we applied in binary addition so that we don't need that linear dependency anymore? So that would be a pretty valid and natural question to ask, because after all, we applied that trick in binary addition. We ended up with carry look ahead adders, which basically give you a constant time to compute any carry bit. Now, the logic gates, if the circuit for the logic gates is messy, okay, for a k of 16, it's going to be quite messy. I wouldn't do it by hand. That's why I have that little generator thing, the formula. But nonetheless, if you write a program to generate the structure of the gate, it wouldn't be that hard to do it. If any one of you is planning to transfer to Berkeley, you will probably have to end up knowing how to program in VHDL or Verilog. Those are the 2 most common HDLs, or hardware description languages. And their job is to describe a circuit. So basically, you write a program that looks kind of like C to describe the structure of your circuit. Instead of doing everything by hand using LogicSim, you're writing code to generate the structure and specifying what connects to what else in a programming language. So with that, trying to figure out k of 64 is not that big of a deal, because we know the structure already. We know the algorithm already. So whether you're trying to figure out K2 or K64, it makes no difference from your perspective. The gate generated, or the logic or the silicon, is going to be more messy for the higher case. But from your perspective, it's like, okay, we just have to call that function with a different parameter, and that's all the differences are. All right, so now we're going to scroll down to borrow look ahead. So this is by definition, regardless of the base. Okay, so regardless of the base, t of I plus 1 is b of xi, yi plus b of qi, ti. So what the first thing we want to do is to ask, can we change this but here with this arithmetic addition to a disjunction? So we asked a similar question for binary addition. So we are now asking the same kind of question for subtraction, which is, can they both be ones? Can b of xi, yi and b of qi, ti both be ones at the same time? Now, to prove this, there are several ways to do it, because a truth table would do it, okay? Because xi, yi, and ki are the only 3 variables that are independent from each other. Qi depends on xi, yi. So you can basically use a truth table that has 8 rows and figure out that, oh, okay, it is not possible for b of xi, yi and b of qi, ti both to be ones. So you can prove it that way, which is very mechanical. but you can reason it out too. Okay, so I'm just gonna reason it out briefly because this class is not about proofs. That's more like a CISP310 thing, but I still want you to kind of think about it and apply critical thinking skills to convince yourself that B of xi,yi and B of qiti cannot both be ones, regardless of the base. So it's not just an observation with base 2, this is regardless of the base. Okay, so let me start with that. What if B of xi,yi is a 1? What does that tell you? What is the implication of B of xi,yi being a 1? If you just look at the function of B, what does that mean? X is greater than y. Xi is less than yi. Okay? So if x is less than yi, what do I know about q of i? So the one thing we know is it cannot be 0, because if it's 0, that means your xi, yi are the same. But the second thing we also know is qi cannot be, let me think about it. Qi cannot be, well, it cannot be a 0. Okay, and that's all we need. Because if qi cannot be a 0, it has to be at least 1. And what about ti? What is the range of value of t of I? T of I is a borrow. It can only be a 0 or 1. So that means T of I can be at most 1. And if x is less than yi, then Q of I is at least 1. Okay, so what does that tell you? Q of I is at least 1, T of I is at the most 1. So can you end up with a borrow of 1 when you subtract T of I from Q of I? You cannot. So we have one half of the proof now. Okay, the one half of the proof is if xi is less than yi, b of xi yi is a 1, but at the same time we guarantee that b of qiti cannot be a 1. Okay, that's one way. The other way is to ask, what if b of qiti is a 1? How do we use that to imply that b of xi,yi cannot be a 1? So think about the consequence. Okay, think about how q of b of qiti can be 1. What is the only case that b of qiti can be a 1, given the range of value of t of I? Q of I has to be a 0. Exactly. So if q of I is a 0, and we know how q of I is computed, what does that tell us about xi,yi? There's no doubt that they have to be the same. So if xi, yi are the same, can xi minus yi generate a borrow of 1? Cannot. So that is the other half of the proof. So now we have just casually, because I didn't write it out, it's not a rigid or it's not a rigorously mathematical proof, but we reasoned it out. Okay, we reasoned out that these two terms cannot both be 1s at the same time. Can one of them be 1? Yes. Can both of them be 0? Yes, but they cannot both be 1s. So once again, if we use a truth table, we will see that the last row, where both of these are 1s, is not going to happen. The first 3 rows will basically say, oh, you can use addition, that works, but you can also use just a logical OR, because it will give us exactly the same result for the rows in the truth table that count. Is that okay? So now we know that this plus here, what looks like an addition, can actually be a disjunction. All right, so that is important because the rest of this part here is they're all Boolean operators. So you don't have to finish, you don't have to follow the actual derivation, even though it's kind of interesting. Boolean algebra is quite interesting because it resembles normal algebra in some of these places, but it also has some really odd thing that you cannot do in regular algebra. But you don't have to fully understand the Boolean algebra. The one thing we need to look at is, we get to this point here. Does that resemble something that we have seen? I did say resemble is not exactly the same, but close. Does it look close to the result of this derivation, the equivalent derivation for binary addition? Pretty close, okay? So this time, we're gonna redefine G and P for binary subtraction. So the G of I is defined to be the negation of xi and yi. And then P of I is defined to be not xi or yi. Okay, so once we redefine P and G with these new definitions, then we get something that is truly resembling something that we have seen before. Because before we saw that K of I plus 1 equals to Gi or Pi and Ti Ki. Now we see that, oh, if you just replace all the K's with T's, we end up with exactly the same structure. Are we kind of following the similarities? So if T of I plus 1 can now be written as G of I or P of I and T of I, what else do you think we can do that resembles what we did before?
When you went to bigger numbers, so people are the third and fourth and whatever.
Say again?
When you get bigger with T, so the next step up.
Yep, we can do the substitution trick, right? So all the tricks that we did with K of I plus 1, we can now do that with T of I plus 1. So we end up with exactly the same structure, exactly the same equations, except all the K's become T's. So remember all those difficult circuits that you did on Thursday? They will work with subtraction as well. Yep.
You would just have to change the G and the P to.
Yes. Exactly. So that means there's a very easy way to convert, to choose between, are we inverting the x before we do the and? Are we inverting the x before we do the or? There's a very easy way to do it using exclusive or. So that means you can make a circuit that resembles what we did with the borrow-lookahead adder. You add one more control bit to specify, are we adding or subtracting? And you can keep the rest of the circuit exactly the same as before. Then you have a general purpose add/subtractor because it can do both. Okay, you use one single bit to control, are we adding or are we subtracting? But the rest of the circuit, the most complicated, which are the individual K1, K2, and the K3 circuits, those remain exactly the same. Because we just have to change the way we compute the P and the G. I think that is pretty cool, okay? Not only have we just figured out how to use transistors, basically NAND2 gates, and then the AND gates, and then the OR gates, and also the NOT gates, to perform addition and also subtraction, we also found that fundamentally speaking, addition and subtraction in base 2, they only differ by this much. Do we negate X first? That's the only question. So are we good? Yes?
So if you're to change an adder to a subtractor, all you need to do is convert the X when finding.
Yep. Do you guys want me to show you how to do that? How to use one single bit and change whether you're adding or subtracting? Yeah. Okay, well, let's do that. All right. So let me start up Logisim first. And then we'll go from there. Looks like I'm gonna have to do it the long way. Right. So just bringing Logisim into your view, which is being recorded. And then we open the circuit here. Okay, so we don't even have to touch K1, K2, and K3 because the only thing we really have to touch is how we compute P, G, and Q. But the only thing we have to do is to insert something between the tunnel X and this particular node here. Because we just have to decide, do we want to negate it first before we do the and the or do we just want to leave them alone? Okay, so that's the only thing we have to do. And obviously the new question is, so how do we do that? So let me go ahead and move things around just a little bit so I have enough space to insert the additional thing. All right, because what we need to do is to get rid of this connection here and then move this thing kind of back here a little bit. So the question is, how do we specify one extra bit, okay, that will specify, are we negating X or not negating X? So you have to think about this something and then doing something with X will either negate it or not negate it. The answer is exclusive OR. So because if X is 0 and that extra control bit is also 0, 0 exclusive OR with 0 is still 0. So it's not doing any negation. Then you think about 1. If X is 1, the control bit is also a 0, then 1 exclusive OR with 0 is still a 1. So when the control bit is a 0, it maintains X the same as before without negating it. And then if the control bit is a 1, then it ends up negating the value of X. All right. Okay, so now we know we need an exclusive OR. So we'll go like, I'm too lazy to make another exclusive OR. So I'm just going to duplicate this one because it already has the correct bit width here. So now we say, okay, we are going to exclusive OR X with something. And then the end result is what is feeding to what X used to feed to. So now the question is, how do we specify this particular control bit? So the control bit has to come from outside. So we have to use an additional thing here to specify, are we adding or subtracting? If we're adding, we do not want to negate. If we are subtracting, we do want to negate. So, or I should say, if we're adding, we want the control bit to be a 0. If we are subtracting, we want the control bit to be a 1. So the name I will give this one is going to be A/S. Now, you might say, oh, that's just your add/subtract. Yes, but it also means to subtract, we want subtract is a active low signal. If we, is that right? If we want to add, no, add itself is negated. Okay, never mind. I named this incorrectly. It is supposed to be S/A. Because the adding one is what we call active load. If we want to add, we want this control signal to be a 0. So this is the proper way to name this particular signal. If we want to subtract, we want it to be a 1. If we want to add, we want it to be a 0. All right. Then you go like, oh, that's easy. Heck, I know how to do this. Just hook this up to the other input of the exclusive OR. And we're all done. No, not really. So what is wrong here is, yes, the control bit is only 1. Why would I want to have 3 control bits when they're all supposed to be the same, right? It doesn't make sense. But at the same time, we have a multi-bit exclusive OR gate here, which is expecting each input to be 3-bit wide. Well, but all those 3 bits are supposed to be the same. How do we fix this problem? Splitter, very good. So we're going to use a splitter in this case. And I don't have a splitter here, but I do have a splitter here that is of exactly the right size. So I'm going to copy it here. Oops, nope, not that. Control-C, copy. And then go to main, paste it somewhere. Oh, okay, it has to choose, paste it over there. And then this time, I'm going to have to flip the direction. So we're going to flip facing to west. Oh, okay, that's not going to work because as it flips, it also makes connections incorrectly. So I'm going to have to put it somewhere else before I flip the direction, like so. And I also wanted to go top down, flip that way too. Let's see. Yeah, maybe not. Okay, close enough. All right, so we now take out this guy here. And this one needs to move, so I'm going to take it out. So now we just say, make them all the same. This is one of the very few rare occasions where you basically take the same single bit and make 3 of those and then merge those 3 because they work together like so. Now we have a adder slash subtractor. By flipping, the subtract slash add pin, I can just change that, change this entire mechanism from being an adder to a subtractor. Okay, if this pin is a 1, it is a subtractor. If it is a 0, it is an adder. The rest of the circuit I'm not giving you because that's what you're going to do today. But this is the only thing you need to change. Okay, so if you start with this file and then you finish the rest of the assignment, then you end up with a 3-bit add subtractor. Okay, but don't do that because otherwise the test driver won't work. The test driver needs to see exactly 3 input pins, X, Y, and K, Z. Yes.
Couldn't you also set the splitter to have only one fan out and then assign that one pin to all 3 output digits of the wire?
I don't think it will work, but we can give it a try. Okay. The reason why I don't think it's going to work is because if you assign all 3 bits to the same split end of the splitter, that split end becomes a multi-bit end, and it's not going to. It won't like to be connected to a single bit pin. So that's what I think it's not. That's why it's not going to work. Question?
I tested it up.
Okay, all right, thank you. Yep, so at that, but the reason is, you can never connect a multi-bit thing, even if it is one of the split end of a splitter to a thing that only has a single bit. So the bit width has to agree between the 2 components. All right. So, yes. Hmm? Yes, P and G only makes sense in base 2. Because the algebra that allows us to go from the original equation to the one that converts the P and G, those are all using boolean algebra. So that's why it won't work in other bases, because all of those derivations only work in boolean algebra. All right. Another good reason why we should teach base 2 in elementary school. All right. Are we good so far? All right. Excellent. So now we're going to move on to, this is it. That literally is the end of this entire slide. However, I do have some people who might be asking, so what do we do with these, right? Well, each one is a loop, okay? So this symbol here is basically a loop. This symbol here is a loop. This is also a loop. So what are we looping? Well, this one here is specifying when I equal to 0, compute this thing here. That becomes a term. And then I bumps it up to 1, compute this whole thing again. I becomes 2, compute this whole thing again. Then we end up with a bunch of stuff, right? N plus 1 impact of those things. What do we do with those N plus 1 things that we generated in each iteration of the loop? Or all of those together. That's it. So are we okay with that concept or not? Because I can just use this generator here to say, oh, let's take a look at T of 2 plus 1, T of 3. So maybe that's going to be a good example. Okay, we can just kind of take a look at how to do this by hand. Because I think once you see how this is done by hand, you go like, oh, okay, I can totally write an algorithm to do this on the way. Or I would hope that you would think that. All right, so I'm gonna choose mousepad, which is kind of like notepad, to illustrate this. Okay. And there we go. Okay. So now we want to compute T of 2 plus 1. There we go. In other words, n equals to 2. All right. So now we have 3 loops, right? Because we have this loop here that is going to stand alone on the side. This loop here has a nested loop, which is this one here. So we basically have, 3 loops. 2 are, one is nested in the other one. So that's kind of the structure. Okay. So we're going to ask, what if n equals to 0? Well, what if I equals to 0? Then we end up with g of 0. I'm going to not use the square bracket, otherwise it's going to be a lot of brackets. So I'm just not using brackets anymore. So we have g0, and then we have g0, g1, sorry. So the next one is when I equals to 1, then we end up with g1. But we also have the other part, which is the big N thing. So this time j has to start with I plus 1. So j starts with 2. So that means we just have p of 2. And then n is 2. So that's the only thing we have. So now we have, so these things become g of 1 and, or g of 1 or, no, g of 1 and, okay. It's an and because the g1 is ended with this thing in parentheses. So it's basically ended with p of 2. So what happens when I equals to 2? Well, when I equals to 2, we start with g of 2. Oh, I forgot one thing, because when I is 0, j starts with 1. So if j is 1, then we have p1, but then j can also become 2, which ends up with p2. So this means we generate a term that is g0, p1, p2. I typed incorrectly here. This is supposed to be p2. Okay, so what happens when I equals to 2? We have g2. So g2 is because I equals 2, this I is 2. But then we look at this thing here, which starts with 2 plus 1. J is 3 to begin with, and is going to 2. We have 0 iteration because the starting index is supposed to be less than or equal to the end index. So if the start index is greater than the end index to begin with, then we have 0 iterations, which means in the last loop, when I equals to 2, we just have g of 2 by itself. So in this case here, we generate g of 2. And now we have these 3 terms, g0 and p1 and p2, v1 and p2, and then g2. The question is, what are we supposed to do with these things? Oh, they are a part of a big OR. So those terms are ORed. So that means now we end up with g0, p1, p2, or g1, p2, or g2. So now we are done on the left-hand side of this OR. Well, now we can work on the right-hand side of that OR, which starts with a t0. But the t0 is ended with the rest, which is in the loop. So that loop says, I starts with a 0, then we end up with a p0, then I becomes 1, we end up with a p1, I ends up with 2, which is what n is. So now we end up with a p2. So that means we end up with a term of t0 and p0 and p1 and p2. And that thing is ORed with the rest. So that means the final answer is to take this part here, which is the left-hand side of this OR here. And then the right-hand side of this OR is basically t0 and p0 and p1 and p2. Is that okay? Does everybody sort of see, how this is done? I mean, I could have easily given you a JavaScript code to do exactly the same thing, but that means you have to understand JavaScript, and I don't think all of you want to learn yet another programming language that looks like C, but not quite. In JavaScript, this would have been very easy to do because you can use arrays, and you can just basically push all the terms, and then in the end, you use a join operation to basically join all the terms with a particular separator, which is either an and or. So that's super easy to do in JavaScript. Is that okay so far? All right, so I just want to convert this into things that you already know, which is C++, okay? It's just really loops in this case. All right, are we good? All right, excellent. So let's go ahead and take roll because today I'm actually semi-prepared to take roll. I took the advice from one of you and generated a QR code. Where is that? Okay, find 2023-0207. There we go. So this is the bit. Oh wait, I have to release it first. Never mind. Don't. I have to. See, this is what I talk to you about in terms of dependency is you have to figure out what to do first, and I forgot that I need to release this first. Okay, so let me do this first. Give me a second, and I got everything else set up already. The access code is XYQTD. Okay, so if you just joined us, make sure you write down XYQTD, which is the access code of the roll taking activity, and then I have to change the time again. I'll give you guys until like 6:50 to do it. All right, save and publish. Now I can show you the QR code. So let me go back and look at the QR code. All right, there you go. Yep, there you go. It should work. It's taking you to a website so I can fish your password too. Embedding cross script, attack JavaScript code into a QR code. So you can either use a QR code or you can just refresh, Canvas and then look for today's date, and you can get to it that way too. The passcode is XYQTD, the 5 rows for subtraction.
Place where you wrote down the notes for the
access code.
The borrows and the R's. Where you wrote down borrow 0, 0 equals 0.
Oh, that?
Yes.
I think I put it into the here, right? And by the way, this particular spreadsheet is already shared with you. So instead of copying, you just need to know where to find it. It's in the shared folder with the name of today's date. Yep.
I think it doesn't allow us to go through. Anyone else found it? But I think it doesn't let us get to that because it's you
Oh, it won't let you get into the.
like the JavaScript.
Oh, it won't let you get into the JavaScript code.
Maybe it's figured out and
If you make a copy, you might be able to do it. Yeah, because okay, in Google Drive, there are 2 ways to set up a document. You can set it up so that people cannot make a copy of the document, or you can set it up, which is by default, where people can make a copy. So in this case, if you make a copy of this, you should be able to get to the script corresponding to the spreadsheet. So you can actually get to see this. And to play with it too. I mean, if you want to change this, so it doesn't work with base 7, instead it work with base 2, that's a quick and easy way to do it. So I do highly recommend that you guys make a copy and then play with it. So you can experiment with different bases, do the calculation by hand first, by yourself, and then use this as a tool to check. Yes.
so just because I use Google spreadsheets a bunch, I did see this. The Google script stuff, that's all in Java.
In JavaScript.
JavaScript. Okay, so I was just wondering as to like what code if you had to write it in and I just never really like figured it out, and so I'm like, okay, whatever, I'll just continue doing stuff, that's how I've been doing it, so just not that asked.
Well, you're only human, so that's a very natural tendency. All right. We have 15 minutes left, so we can get started with compare, well, let's see what the next module is. Where is it? All right, so we are done with subtraction. Subtraction. So the next one has to do with signed versus unsigned integer representation. All right, so this one has to do with, if I just have a bunch of zeros and ones, I know how to do base conversion, so I have no problem representing integers that are non-negative, right? Yes, no, okay. For instance, okay, using an example, if I want to represent 13, okay, I just have to figure out, okay, 13 is a sum of which powers of 2? There's an 8, there's a 4, there's a 1, right? 1 is 2 to the power of 0, so that's digit 0. 4 is 2 to the power of 2, which is digit 2. And then 8 is 2 to the power of 3, which is digit 3. So all of those digits, okay, digits 0, 2, and 3 need to be ones. And then the only one left, which is digit 1, needs to be a 0, because there are no 2's, in 13. So I don't have a problem converting a value into a base 2 number, as long as that value is not negative. Okay. So now we need to look into ways to to represent values that are actually negative. And that's what this particular module is about. So the first thing is, when you're in your math class and then you ask your professor, what is the largest integer that I can use in this class? The professor will just look at you very strangely and go like, don't you think there's an infinite number of integers? Because if you tell me this is the largest integer, then I'll tell you what is 1 plus that. Okay, but in this class, if you ask, what is the largest value we can represent in an integer, I can actually tell you what it is. Why? Because in programming, all the variables have a fixed width. Okay, in C++ at least. Okay, there are some languages that has variable width integers, in which case, the largest integer value can be really big because it really kind of depends on how much memory you have. But in C and C++, it's fixed width. It can be 8, 16, 32, 64, and I think these days up to 128 bits. I mean, a 64-bit number can go really, really high, but it is still finite. Okay, so there is always that answer of what is the largest value we can represent given a certain number of bits. So the way we figure this out is the answer is already here. Okay, so if you read this part here, this is for unsigned. Okay, if W is representing the number of bits, okay, which is 8, 16, 32, or 64 to most programs, then 2 to the power of W minus 1 is going to be the largest integer value that you can represent as an unsigned integer. Why do we need that minus 1? Because 0 is taking up 1 spot. So that's why we don't have, in order to use all the spots, which is 2 to the power of W, that's the number of spots that we have. But because one of them, because we start counting from 0, so that means the largest value is 2 to the power of W minus 1. So if you just make W really small, it makes it easier to look at or easier to visualize. So when W is 4, then 2 to the power of 4 is 16, 16 minus 1 is 15. So what we know as 15 is the largest unsigned integer that you can represent if you're only given 4 bits. Is that okay? Because it is 1, 1, 1, 1 in base 2. Is that okay? So now we want to think about, okay, what about negative values? How do we deal with that? The most natural way of thinking is to say, oh, we just need one bit to specify, whether the rest of the bits are specifying, whether it's a positive or negative value. That's a very natural way of thinking about it. It's a very simplistic way to say, oh, we can now represent negative values that way. But as it turns out, that is not a very good way of representing negative values because we cannot reuse the adder and the subtractor that we already have. Okay, so we want to find a way to represent negative values such that the adder and the subtractor thing that we have worked out continues to work. Okay, so the tricky answer is to take a look at how 19 is going to be represented as a 4-bit number. Or start with this type of thinking. So you can think about, instead of a number line that stretches out infinitely on both ends, think of it as a number wheel. Okay, the number wheel in this case has 16 spots. So we have 0, 1, and then here is going to be 4, here's going to be 8, here's going to be 12, and then back to 0. Okay, so instead of a number line, we have a number circle. So we ask, what is 19 on this number circle? So you start with 0, you go like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. In other words, 19 is sharing the same representation as 3. So in mathematics, there's a term to refer to this type of thing. It has to do with, okay, that term always escapes me because it's not a concept that I usually pronounce. I think it has to do with congruent. There we go. So it's called congruent modulo, which means whatever you do, we're just going to mod, that whole thing with whatever base we're working with. So in this case, when we're using 4 bits, we're actually working with base 16 because there are 16 slots on that wheel. Okay. Now underneath, you might be using base 2 to represent all those values. But when we're looking at this from the perspective of congruent modulo, we are looking at 16 as the base. All right. So the way we write down 3 and 19 are congruent modulo is to say 3 is equivalent to 19 congruent modulo 16. That's why the equivalence has a little subscript of 16 because we are saying, hey, if you mod everything with 16, 3 and 19 are really the same thing. Because 3 mod 16 is 3, 19 mod 16 is also 3. What else mod 16 is also 3? 35, okay? And in fact, 3 plus n times 16, okay, as long as n is an integer, all of those integers would be considered equivalent or congruent modulo 16 because they all end up at exactly the same spot on the wheel. Is that making sense so far? Okay, it's just a weird way of looking at these things are all the same because if we just kind of keep swinging our arms like this, they all end up at the same spot. Yes.
So is congruent modulo that notation there? Is that what we represent it as?
Right. So if we are looking at mod 16, congruent modulo 16, then 3 and 19 can be considered to be congruent modulo 16. So congruency is kind of the same thing as equivalency, except in this case, we have this little attachment of saying, but only when you mod that thing with 16. Are we good so far?
It's like hashing the thing.
So hashing does make use of the mod operator, and so it is related to hashing. So if 2 values are congruent modulo however big your hash table is, then you have a hash collision. So yes, you can relate this concept to hash it in data structure, which is CISP310. So that's very good. Relating concepts between classes is a very useful idea, because this way you're making you're connecting a bigger mesh of all the concepts that you have learned already. That is good. All right. So the question is, why do we care? So the question is, why do we care that 0, 0, 1, 1 can represent 3? It can also represent 19. That is silly. Okay, that is just silly. But is in addition to doing it this way, being modular congruent, it can also work the other way, like that. Okay, so let's think about this. Okay, so I know this is not getting recorded, but you can probably still kind of have a mental picture. So this is 0, right? Going in the clockwise direction from your perspective is going up. So what does it mean if I go counterclockwise? It's a subtraction, right? So if this is 0, this is going to be -1, -2, -3, -4, -5, -6, -7, -8. Does that make sense? So let's just pick one of those positions. So this is 0, -1, -2. So think about the -2 position. Now you swing your arm in a clockwise fashion and see when you get to that spot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 and -1 are also congruent modulo 16. Now this one is interesting because, so that means the same bit pattern, which is 1, 1, 1, 0, that can be used to represent 14, can also represent -2. But it cannot represent two things at the same time. So here comes another puzzle, which is kind of a mental trick, which is if I'm just looking at a bit pattern of 1, 1, 1, 0, does it mean 14 or does it mean -2? You guys won't like the answer. Okay, so the both is kind of like a quantum physics sort of answer. The answer is, why do you care? Why do you care? Because if you are looking at 1, 1, 1, 0 and just say, oh, so that means three bright pixels and 1 dark pixel on the screen, why do you care whether it is -2 or 14? You are just specifying 4 pixels on the screen. Does it matter? Are you guys following the reasoning? Do you guys know what is a dot matrix printer? Okay, most of you are way too young. Even your parents may be way too young to remember what a dot matrix printer is. A dot matrix printer is basically, it has a vertical column of pins. Each one can be activated individually. So you can have pins extruding and retracting and whatnot, and they're all independent. And then you have a ribbon, okay? And then the ribbon goes, and then the print head with all of these pins also go. So this is how we print things in the dark ages. Okay, you have a piece of paper behind the whole thing. You have paper, ribbon, and then the pins. So when the pins extend, it will basically put a dot on the piece of paper because of the ribbon. Okay, so 1, 1, 1, 0 can easily also be used to specify, oh, those 3 pins are extending and this pin is not extending. So we end up with 3 dots on the piece of paper. And how does that have anything to do with 14 or -2? So until you really need to know, so the only time it makes sense to say, is 1, 1, 1, 0 a -2 or is it 14? Is when you compare. Because when you compare 1, 1, 1, 0 versus 0, 0, 0, 0, then the interpretation matters. Okay, In other words, let me make this more clear, clarify. If I'm asking you, is this bit pattern, which turns out to be 1110, is it less than this bit pattern here, which turns out to be 0000? Then you have to ask the question, because the concept of comparing means, oh, okay, I need to know what value these particular bits are representing. 0000 is always just representing the quantity of zero, so that's an easy one. But 1110 is not, because 1110 can represent 14 if you choose to look at it as an unsigned integer. But it can also represent -2 if you choose to look at it as -2. And depending on whether it is interpreted as 14 or -2, the answer to that question, whether this bit pattern is less than this bit pattern, will be different. So it's only when you are comparing that you need to know, is it -2 or is it 14? For everything else, there's no difference. If you want to add, it doesn't make a difference. I will show you next time, okay? Why adding does not make a difference, whether it's signed or unsigned. Okay, adding does not make a difference. Making a copy doesn't make a difference. So in C and C++, the sign is associated with the variable, right? But in the end, when you're looking at the computer architecture, nobody cares about the signedness until we have to compare. So in assembly language programming, which is not going to happen for another 4 weeks or so, we don't really care about signedness until we get to certain instructions. When you declare a variable, when you reserve the space for a variable, we don't care. We just have to ask, so how many bits do you want to reserve? 8 bits? Okay, fine, here's 8 bits. I don't need to know whether it's signed or unsigned or what it is. I just need to know where it is, how many bytes, how many bits we have allocated. It's only when you compare and need to know the result of the comparison, then we care. All right, so that's the end of today's lecture. Yes, your reading assignment. Okay, I still need to give you the access code of tonight's lab and stuff like that. So give me a second. All right, so today's lab is part 2. It's called 3x3 carry look ahead adder part 2. And you will need to know the access code. So the access code is 3x3b or lowercase. And the time is already set up. I'm just going to save and publish. There's also a file submission, companion to this. So make sure you do that one too. I'll see you guys at the lab in 10 minutes. Three X3B. Yep. 3x3b. Okay.